So we have fountains, garden fountains. Okay, basically you can see very popular in these theme parks, hotels. Okay, so it can be analyzed if, of course, it is 3D geometry, right? So, but a lot of time it can be basically is axis symmetry geometry. So basically you can what we call analyze in what we call 2D, okay, axis symmetry element under an axis symmetry. Then the load itself is also axis symmetric. The support is also can be axis symmetric, and this 2D model can basically slide through from a 3D geometry. And we look into this our so-called, if you still remember, hold on, we have this so-called R. We have this basically our R. Basically this is our R. This is our Z-axis. So a lot. It basically is an axis symmetry problem. It can be analyzed under axis symmetry problem. So basically this figure itself is a cross section of an axis symmetry model of two-tier garden fountain made of concrete. So we want to determine the maximum deformations and the stresses, okay, normalized stresses under a given hydrostatic pressures. So this hydrostatic pressure or from the water itself, basically it happened at the dot line okay, at this. So we use, okay, the question basically this problem basically use adaptive meshings to improve solution convergence. I have tried, okay, both, okay, space claim and design modeler. So probably you can also try it later on. So what we can do here is under this engineering data, right? So we have to create a model, create a materials lah. I don't know whether you can see or not. Wait, okay, so you can see it. Then we put a concrete. Okay. First we create models. Then here we need the Young modulus and also the Poisson ratio. So under isotropic elasticity, you double click on it. Then we have to key in. The Young modulus is, hold on, let me check. The Young modulus is 29 E9 and Poisson ratio is 0.15. So I put 29 E9. Poisson is 0.15. Right, so that is done. Then we can start to model it. So try with space claim. So here, if you look at here, so we choose solid bodies. We check already. Under this geometry just now, right? Yeah, I have to. Before you start the space claim, I mean, you have to make sure you have checked the surface body. So here, surface body, line body, we don't need already. But here, analysis start, you have to select 2D, two-dimensional. So later on, in the under mechanical later on, you will see the two-dimensional types of elements. Then we can model it. So it will be opening a space claimer. All right, so here, of course, we change the units, everything correctly under options, space claim options, units. So we can change to meter, right? Then here we put 0.02 so that we can draw it, the grid easily. Then we can create a new sketch planes. Okay, click on this, or I think at here, right? then you have to choose the plane. So here we are choosing XY plane. Right, so when you choose the XY plane, just click on it. Right, then you have a plan view. So now we are in the XY plane. All right, so we can start drawing under design. The line itself, we can start drawing according to the dimensions that given this surface body of this fountain itself. So under here, we click the line, right? Then we can start draw from this the origin axis. So we go here. Okay, so 1 meter. The base is 1 meter, so I will just choose 1 meter. Right. So then it go up 0.2 meter, so 0.2. Then it comes here 0.06. Okay, so yeah, it's already 0.6. Coming down 0.12. And going back here is 0.8. And going up here is 0.5. Then you have a 0.6. And going up here is 0.2 again. Right. Then here is 0.06 again. And coming down 0.12. Then straight to the Y there basically. Right. Straight to the Y here. This point itself up here is around 0.1, 0.68. Right. Then coming down here is 0.66. Okay. Right. So that basically gives you the curve of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So if you want to look at its dimensions, so probably you can go to under detail tabs. Right? So we have the dimensions here, so you can click on this. So to check, the dimensions. Just now we have checked already, so don't, you not so necessary. So once you have done this, okay, then you go to, if you have checked, satisfied with all the dimensions, then we have to do this so-called billets, the curve, here, 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 and these two. So what we do is we go to design, right? So you see this, right? Create a rebound corner. So you just click on this, then we just select this select a line to here. So then you choose 0.1. Right. So that gives us this. Again, here the radius is 0.1, so basically the diameter is 0.2. So we can choose here and here 0.1. So here again to here 0.1 there, right? So 1. Then you have okay. So that basically gives us the what we call the curve Then what we are doing now is basically under design itself. Then you just click pull. Then it will basically create the surface bodies. Okay, so if you click on this itself, then this is the surface body that we want, right? So you can basically close it, then you can go to the models, right? So under the model itself, okay, you will go towards the what we call the mechanicals, under mechanicals. So that is your models are coming up, okay, in three, basically like this. This is just a surface models. So here, basically that is what we have lah. Then what you need to do is under geometry here, we have to change this 2D behavior from a plane stress model to axisymmetric models. Right? Under this surface body itself, we have to assign the correct materials. So under the material assignment from a structural steel, we choose the concrete. Then next will be the meshings. So unlike our previous so-called case studies, so we don't have a local settings, we all use global settings. So if I suppress this just to show you. Okay, so previously we have this, then we under the element size, we just put whatever default numbers, right? So everything is auto, right? Even the types is under the type of the mesh is also auto. Right, so here probably we can call this out. So what you do is right click, insert sizing, right? So once it insert sizing, then it basically come out with this unsuppress. Let me show you. It will come out with this where you select the face lah. So here you choose this under here, you have to choose the face lah, the entire face. So basically it's a face sizing. Then under the element size, we put 0.05 meters, right? According to the questions, right? Then the next part is the methods. So if you go through inserts, okay, you click methods, then this thing will come out. So this is where you set what type of from here you also have to choose you have to choose this body itself. Okay, you click this apply, then you basically select this body, okay, the entire body, then you choose the methods that you are using. Okay, so here I'm using triangles. So element orders, okay, you can either choose here, okay, or use global setting. So global setting means you have to come back to here, global setting. So global setting under element orders, I put linear. Okay, so that is also whichever way you can use. So usually we put at here we can choose the linear. So you won't see that mid side node cap or drop in the latest versions. So what we do now is just generate mesh. Once we have this setting, we generate mesh. So basically, this is the mesh that it is generated based on the. All you see that is triangle types, and here is a linear. So even you are putting quadratics, you won't see it but you won't see a node there but it's basically under quadratics. So if I put here under here, if I generate mesh. Also the same, but it's a second order the quadratic functions, or in between the node itself. It's there, we won't see it. So we put linear. So if you are looking into, if you touch stress by right, you should use quadratics So here we are just demonstrating the adaptive meshings. And we are using total displacements to adapt the meshings. So here we try to use linears faster. So we have a fixed support. So you go to right click, inserts a fixed support, okay, at the base. Okay, so if you click fixed support, so that is at the base itself. At here is a frictionless, okay, supports where you have the axis. So means basically you won't allow a movement, a motions along this particular axis itself, or normal to this particular axis itself, the surface itself is not allowed to any deformations. So that is what we call frictionless supports. Then load, no? We have to apply load. So you go to inserts, then probably you have these hydrostatic pressures, okay, where you have to apply. So under here, hydrostatic pressure itself, we have to select the edge, I mean, this geometric edge. So here we are selecting the curve. So if you look into it, is this curve and this curve, okay? So that is where you have your waters, right? Moving the waters, okay? This curve and this curve, right? Then we have to put in the fluid densities, okay, waters. Then the acceleration here basically is 9.8 in the y-axis, which is our gravity, okay, 9.8. Then we have to put the locations, free surface location. Where is our free surface location? Meaning the top layer of our fluids. So we need to define these coordinates. So what we can do basically is at this particular point, let me show you how. Okay, so just now we select this curve, So our top surface of the water is basically this node itself. So what we can do is, if you know it, then you can key in the XY of that coordinate. If you do not know, then basically you can click on this select vertex. Then you click on this, right? So under selection information, from detail, you go to selection information. Then you know that your X coordinate is 0.68, Y is the global is 0.76. Basically, our origin is at here. So basically, it's 0.68, 0.78 is this point. So what we do here, the top surface of that particular water, I mean, we can insert 0.68 and 0.7. Sorry, just now is 0.68 and that means 76, right? It's a 0.76. So here, if you look in, I think my model for this particular case, got some changes. Okay, so if I'm going towards the geometry, it's 0.68 and 76. So here I have to choose under here is 0.68 and 76. Then at the same time, we have the second one. Okay, we have the second hydrostatic pressure at here, this curve. Okay, talking about this curve, and this curve, and the top layer is at this particular point, which is happening at 0.94 and 0.18. Okay, 0.94 and 0.18. So what we do here is we select the three edges, the three curve, then fluid density together with the y component acceleration and 0.94, 0.18, which is my top surface. All right, then the load is there, right? The load is there, the support is there, and the mesh is done. The material is there, the geometry is there, so all are there. So actually we can call to solve deformation, total deformation. Okay, and even if you want to look at stress also can. Equivalent stress is the Burmeister stress. Then at the same time, I mean, the question said we have to use adaptive meshing, you still remember. So here is where you, after you call the deformations, total deformations, so this thing will come out. So under this total deformation, you right click, insert, okay, here, hold on, so let's say I'm showing you here, insert deformations, total deformations. Then here, insert, you have this convergence, right? So you click on convergence, then that is this thing coming out. Hold on, this coming out. So this is where you do the additional setting. So the allowable change is 1%. So we change to 1%. So meaning any subsequent iteration where this total displacement less than 1%, then it will automatically stop lah. Oh. So at the same time, under these solutions, we also under this adaptive mesh refinements, we put a maximum refinement loop is 10, right? So the refinement depth is 1. It can go up to usually can go up to in between 0 to 3 lah. So it's more towards how aggressive you want to refine it lah. Oh, so larger number means more aggressive lah. So in this case, we just put 1 as indicated by this problem case studies. Then at the same time, we call this equivalent stress. We want to look at the equivalent stress also. So once all this done, then we can click solve. So you will see that when it's solved, it is actually going through iterations now. So you see this, it finish, then it comes the second iterations. It takes some time now. All right, so basically you have a few iterations every time you see it. So later on we will check the results. Okay, so all done. Okay, it's converged. Okay, you managed to converge. So under conversion, you can see that your tolerance, the displacements it started from the first iteration. It started from 4.3, which is our original mesh size. Start with 4.3. Then when it refined by itself, okay, or adaptive refinement. So it tries to refine it, then it will go to this 4.8, 7 somethings, okay, to 8. Here is 4.81. Then it go again, it will go to 5.1. Go again. The fourth iteration is 5.2. Then at the end, the fifth iteration is 5.23. So this between these two is less than 1%. Then basically it converge, consider converge and stop lah. Okay, so the change is basically less than 1%, so it stopped. So the nodes basically it increase. We are using linears, so we are only under H refinements. So here from 165232 originally, if you look into here, element 165332, this is 16532, 165 node 232 elements, right? So it slowly increase, refine. Okay, 226, 340, 408, 669, 1050, 1882, 22. At the final fifth iteration is 2228 and 4157. Okay, so that is where you get your change of displace total deformation is less than 1%. So it stops. Okay, converge. So the deformations is something similar like this, and the mesh, if you look at here, basically it refine particularly. You see that is here, especially here, still linear. Okay, still linear triangular mesh. Okay, but then particularly at here, you try to refine, and you have a more larger motion. It basically try to refine smaller, right? So at the end, you get after fifth iteration, you get this is your so-called total deformations. Then at the same time, you can have your equivalent stress, right? You have your equivalent stress. Okay, so you can play it. So basically it's around point. The maximum is happening at here, right? So talking about 0.1, basically is around 0.1 megapascal. All right, so the problem, the case study also allows, okay, go further. After this, it go further to include more loads, more types of load where you have probably the gravities, the weights of this concrete itself. Also consider you have the weight. You consider the weight of the concrete itself as well as the what we call the rotational parts. Here is talking about the centrifugal's inertial force. Because this is axis symmetric. So you have a line here. So basically, you also consider basically if you're undergoing a rotational so-called force. So you consider the weight of the concrete as well as what we call this centrifugal rotational force. So in this case, you need the mass of this particular concrete itself, right? Then we need to put in the what we call the densities, right? Previously we didn't put the density, right? So if you look into this geometry itself, the properties itself. So you don't have volume, you don't have mass, you don't have all this information. You only have the surface area is approximate 0.231218, right? Here, if you put in your densities, okay, so under going back to here, engineering data, right? So here we didn't put under structural steel, you see you have the density, right? Under concrete, we only put isotropic elasticity. So if you put in density, then probably you will have information of the mass. Then you can calculate the weights, the standard gravity, include the standard gravity to calculate the concrete weights as well as the centrifugal inertial force. So additional loads, okay, then probably together with the hydrostatic pressure itself, the load itself, you have more load, then probably your deformations will be larger. So in this particular problem later on, if you follow the case study, it will show that you have a larger deformations. All right. So if I compare my so-called space claims with the model of my what we call design modelers. So although the areas surface areas are same, so it will still see you will still see some variations or the difference between the tools. So if you later on, let me show you this one. Right, can you see it? All right, so if you can see this, I have two models. Okay, one, I forgot which one. A is my space claim. So this B is my design modelers itself. So it's basically the same. So if I go to the surface body itself under the properties, right? So it's a 0.23218. So also the same from what I have here. Okay, properties 23218. So everything is the same, considered same. But then in terms of even I use the same meshing methods. In terms of discretizations, it will be a slightly different. So you can see the mesh, how it discretize, basically it will be slightly different. It depends on the way I model it of the models. So there is some difference in terms of discretization because you see that it's start at particular here and here will be a little bit difference, okay, especially at these particular regions. Right. So the result wise, okay, everything the same setting, I put the same. Then the result wise, I probably you will see maybe 313. Here is 0.2 So it's 0.2247. Okay. Then in terms of you see the adaptive, because this particular part just now is a little bit different. So in terms of refinements also, you will see also here will be you see in this particular part for space claim is final compared to here. Okay, so in terms of at the end the convergence tables, so you can actually see that even at the beginning itself, the refinements is slightly different. I mean the mesh 165, 162, 226, 232. Then now at the end you have 2228 to compare to this. So it's slightly different in this case. So you have a lesser elements, right? So you have lesser elements than you have yeah, in this case. So you can check, okay, let me know your results, okay. Maybe my models is not that accurate using design modelers or what. Let me know, okay, so you can try it lah, probably later on. All right. So that is about this case study where we cover two-dimensional elements here, okay, especially an axis symmetric problems. Then here we are also dealing with adaptive meshings, okay. So here we can help us to so-called refine our mesh so to get a more consistent results. Like in this case is we said more accurate result because we have a final mesh and it converges based on the 1% total displacement deformations between the previous iterations, so that we have set.